The Robust Incomplete Deep Attack Framework, RIDA, is a novel algorithm designed to enhance the security and robustness of graph neural networks, GNNs, against various adversarial attacks. GNNs are crucial in data science, but they are susceptible to such attacks, particularly graybox poisoning attacks, which cause significant performance decline through small changes in the graph structure. These attacks require GNN models to be regularly retrained with new data, making them a primary threat. Existing research on graybox poisoning attacks primarily manipulates the adjacency matrix as a modifiable parameter, using a loss function that opposes the regular training loss of target GNN models. However, this research focuses on complete graphs, overlooking the real-world scenario of incomplete graphs. RIDA addresses this gap by introducing a robust graybox poisoning attack framework that can effectively handle incomplete graphs. It innovatively aggregates distant vertex information and ensures powerful data utilization. The approach is tested against 9 state-of-the-art baselines on 3 real-world datasets, demonstrating its superiority in handling incompleteness and achieving high attack performance on incomplete graphs. The paper also discusses the limitations and assumptions of the proposed framework, highlighting potential avenues for future work. It emphasizes the importance of developing robust GNN models that can withstand various attacks, enhancing their security and reliability in critical applications. In the realm of graph neural networks, GNNs, current algorithms face challenges when dealing with incomplete graphs, particularly in scenarios where a significant proportion of vertices lack sensitive attributes. This paper introduces the Robust Incomplete Deep Attack Framework, RIDA, a novel algorithm designed to overcome these challenges and achieve robust graybox poisoning attacks on graphs with incomplete attributes. The proposed model consists of 3 modules: Depth plus GNN module, Local Global Attention module, and Holistic Adversarial Attack module. The Depth plus GNN module is tailored to enhance the aggregation range of vertex attributes, maximizing the utilization of existing attribute information. The Local Global Attention module considers attributes from both global and local perspectives, fine-tuning the model's focus during the aggregation process. Lastly, the Holistic Adversarial Attack module utilizes the refined information from the previous modules to conduct comprehensive adversarial attacks. The authors conducted extensive experiments on 3 real-world datasets, comparing the performance of RIDA against 9 state-of-the-art baseline algorithms. The results demonstrate that RIDA outperforms the baselines in scenarios involving missing attributes, showcasing its potential to provide valuable insights for the design of robust GNN models. The paper also provides a preliminary explanation of foundational concepts, including attributed graphs and GNNs. An attributed graph is defined as G equals V, E, X, where V represents the set of vertices, E denotes the set of edges, and X is the attribute matrix, with each row corresponding to the attributes of a vertex. In versus GNNs are summarized as models that iteratively generate a vertex's representation by aggregating those of its neighbors, with the main differentiator being their unique aggregation and combination methods. The problem definition for RIDA is to challenge the effectiveness of GNN models globally in semi-supervised vertex classification. This is achieved by perturbing a limited subset of edges in the dataset, less than a small rate epsilon, to mislead the target model into developing a lower quality model. The authors focus on the scenario where the majority of vertices lack certain sensitive attributes, introducing 2 critical parameters, alpha and beta. Alpha represents the proportion of missing attributes in each vertex with incomplete attributes, while beta represents the proportion of all vertices with incomplete attributes. The information available to the attacker is limited to G equals V, E, X phi, and Y, where X phi is the attribute matrix with missing rates, alpha, beta, and Y is the set of vertex labels with a much smaller quantity than V. In conclusion, this paper presents a novel algorithm, RIDA, which is specifically designed to address the challenges posed by incomplete graphs in GNN security research. By introducing innovative modules that enhance attribute utilization and adapt to incomplete graphs, RIDA demonstrates superior attack performance compared to current state-of-the-art algorithms in scenarios involving missing attributes. Enhancing the robustness of graph neural networks, GNNs, against attacks, particularly on incomplete graphs, is crucial for their reliability. The proposed framework, RIDA, prioritizes two essential aspects: extensive propagation of attribute information and robust noise suppression within the data. A simplified version of the graph convolutional network, GCN, is employed to mitigate the oversmoothing problem that occurs when aggregating attributes from distant hops. The depth plus GNN model initializes vertex features to suppress noise from incomplete attribute data and utilizes a multilayer perceptron, MLP, for effective feature mapping. The depth plus GNN maintains a time complexity of O, E, for attribute propagation per layer, where E denotes the number of edges. To prevent reinforcing the significance of a vertex's attributes, self-loops are removed from the adjacency matrix. The formula for the depth plus GNN is derived as x, k, equals x, if k equals 0, lambda caret ax, k1, plus 1 lambda, x, k1, if k greater than 0, where a caret represents the normalized adjacency matrix excluding self-loops. K element of Z is greater than or equal to 0 denotes the number of aggregation layers, and lambda equals delta, 1 gamma, caret k. The parameters delta and gamma govern the strength of weight decay for each layer during iterations, ensuring adaptive control over the weights assigned to aggregate features and effectively reducing oversmoothing. The depth plus GNN model offers a robust solution for enhancing the resilience of GNNs against attacks on incomplete graphs. By utilizing a simplified GCN structure, removing self-loops from the adjacency matrix, and employing an MLP for feature mapping, the model provides an effective approach for improving the robustness of GNNs. The proposed RIDA model incorporates two key modules: the local global aggregation module and the holistic adversarial attack module. The local global aggregation module enhances the model's ability to merge data across varying distances by applying attention-weighted residual embedding to each known attribute. This is achieved through a bifocal feature processor, which preserves original attribute information and mitigates oversmoothing. The holistic adversarial attack module is designed to find a perturbed graph that minimizes the attacker's loss when training a surrogate model on this graph. This is accomplished through an optimization technique involving a perturbation matrix, which induces structural perturbations to the dataset. The objective is to transform the problem into finding a perturbation matrix while ensuring the proportion of differing edges between the original and perturbed graphs is less than a specified threshold. To achieve this, the authors employ a surrogate model to replace the invisible target model and utilize gradient descent to optimize the input feature of the surrogate model. This approach enables the RIDA model to effectively merge data and generate robust perturbations, ultimately enhancing its capabilities in graph-based data modeling. This research paper introduces a novel framework for robust incomplete data attacks, RIDA, on graph neural networks. The proposed method leverages an optimization strategy to enhance the effectiveness of attacks in scenarios where vertex attributes are missing. This is achieved through a surrogate model that approximates the target model's behavior, allowing for more precise and efficient attacks. The experimental setup includes 3 real-world datasets: CORAML, Sightseer, and Cora, each with varying characteristics. These datasets are split into labeled and unlabeled vertices, with the latter being used exclusively for evaluation purposes. The attack models are compared against 9 state-of-the-art graybox poisoning attack algorithms, including DICE, EPO-ADIG, GRAD, PGD, and several variants of meta-based algorithms. To further validate the advancement of RIDA, the authors compare it with 3 baselines from the A-metaself model, including mean, KNN10, and KNN100. Additionally, they assess the effectiveness of the optimization technique by comparing RIDA with OFE, which uses the optimization strategy without the surrogate model. The attack effect experiments are conducted under 2 different settings for the parameter beta, 0.7 and 0.9, and 2 settings for alpha, 0.1 and 0.3. The results indicate that RIDA consistently outperforms other algorithms, particularly when a significant portion of vertices attributes are missing. It achieves an average reduction in target model performance of 4.89% and 4.33% at alpha values of 0.1 and 0.3, respectively, when beta is set to 0.7. Similarly, at beta equals 0.9, RIDA reduces the target model's performance by 3.82% and 3.88% for alpha values of 0.1 and 0.3, respectively. These findings suggest that RIDA can effectively mitigate the effects caused by incomplete information, demonstrating superior attack performance compared to previous algorithms. The paper's experiments and results highlight the importance of considering incomplete data scenarios in the development of robust graph neural networks. The authors of the research paper present an evaluation of the attack efficacy of various algorithms on three datasets CITESEER, CORA, and CORAML. These datasets are tested with different target models, including GCN, GAT, and SAGE. The attack efficacy is measured at two different settings of hyperparameters alpha and beta, specifically alpha equals 0.1, beta equals 0.7 and alpha equals 0.3, beta equals 0.7. Tables 1 and 2 in the paper compare the performance of 12 different algorithms, such as DICE, EPO, ADIC, GRAD, PGD, meta-self, meta-train, a meta-train, a meta-self, a meta-both, KNN10, KNN100, mean, RIDA with and without feature engineering, FE, and the clean model. The results indicate that a meta-train and a meta both achieve the highest attack efficacy across all datasets and target models, with a meta both performing slightly better. The authors note that a meta-self maintains a degree of effectiveness at beta equals 0.7, but its performance deteriorates significantly when beta equals 0.9, falling behind GRAD. This is attributed to the ineffectiveness of the self-learning component of a meta-self in scenarios where a substantial number of vertices lack attributes. Overall, the results suggest that the proposed AMITA algorithms outperform other state-of-the-art methods in terms of attack efficacy, but their performance can be affected by the choice of hyperparameters and the quality of available attributes. The authors present a comparative analysis of the attack efficacy of various algorithms on incomplete graphs, focusing on GCN, GAT, and SAGE models across CITESEER, CORA, and CORAML datasets. In tables 3 and 4, the authors compare the attack efficacy of different algorithms at varying parameter settings, alpha and beta. At alpha equals 0.1 and beta equals 0.9, the proposed attack framework, RIDA, outperforms other baseline algorithms, including DICE, EPO, ADIC, GRAD, PGD, and meta-self, in terms of reducing the accuracy of the target models. Similarly, at alpha equals 0.3 and beta equals 0.9, RIDA demonstrates superior performance in reducing the accuracy of the target models compared to other baseline algorithms. An architecture ablation study is conducted to assess the model's capacity to extract refined information from incomplete graphs. The experimental results, presented in Table 5, involved testing the effectiveness of different modules in the RIDA framework, including the self-learning component, BFP, local and global attention components within the local global aggregation module. The results are evaluated using the accuracy metric, where a higher value indicates the model's capacity to deliver superior information from incomplete graphs. The ablation study results in Table 5 demonstrate the efficacy of the complete model across three datasets, with the inclusion of any module enhancing the performance of the depth plus GNN module. Notably, the local attention mechanism outperforms the global attention mechanism in terms of performance improvement. Further analysis in Section 4.4 presents two additional sets of experiments on the CORA dataset, assessing the robustness of RIDA. The first set evaluates the attack performance of various algorithms across different values of beta, with RIDA achieving superior attack performance in all scenarios. The second set examines the benefits of increasing the depth of RIDA's modules. Figure 4a illustrates the information refinement capability of RIDA's modules under various scenarios, demonstrating substantial performance enhancements with the addition of more layers across all scenarios. Figure 4b presents the attribute propagation of the model when k equals 16, showing that information is transmitted between almost every pair of vertices in the graph. This highlights the model's ability to effectively propagate information across the graph structure. The Related Works section provides a comprehensive overview of adversarial attacks on graph neural networks, categorizing these attacks by task level, purpose, stage, attacker's insight, and perturbation nature. This highlights the complexity and diversity of these attacks, emphasizing the need for robust defense mechanisms like RIDA. The authors introduce RIDA, a novel model designed to achieve robust vertex-level untargeted graybox poisoning attacks on graph neural networks, GNNs, with incomplete attributed graphs. This model addresses the challenge of incomplete information in noisy data by aggregating information from distant vertices and reducing the influence of noisy information through a powerful attention mechanism. Previous works, such as meta-based attacks and PGD, have employed meta-learning approaches and first-order optimization methods, respectively. However, these algorithms failed to perform well on graphs with missing attributes due to incomplete information and the influence of noise. In contrast, RIDA is the first method to achieve robust vertex-level untargeted graybox poisoning attacks on incomplete graphs. The authors demonstrate the effectiveness of RIDA through extensive experiments against 9 state-of-the-art baselines on 3 real-world datasets, showcasing the robustness of RIDA in scenarios with missing attributes. This research contributes to advancing the security of GNNs in practical applications, highlighting the importance of considering incomplete and noisy data in the development of GNN models. Please provide the content to refine, and I will transform it into a direct, concise form suitable for voiceover narration, maintaining technical accuracy and depth, and adhering to the guidelines you specified. It seems like you didn't provide the content to refine. Please provide the transcript you'd like me to refine, and I'll be happy to assist you in creating a concise, technically accurate summary for voiceover narration.